What if you removed every machine learning library? No TensorFlow, no PyTorch, no OpenCV. Just pure C++, math, and a deep understanding of how neural networks really work. Hey everyone, I'm Robert. Join in and welcome to my brand new series, where we built a convolutional neural network completely from scratch, not just to make it run, but to truly understand how it works under the hood. Today, deep learning looks simple. You import a framework, define a model, and train it in a few lines of code. But that simplicity hides the hard part. Behind every deep learning framework are thousands of lines of logic, tensors, convolutions, gradients, optimizers, numerical stability, memory layouts, and training behavior. This series exists for one reason: to open the black box. Instead of using a framework, we're going to build one. When I say from scratch, I mean from scratch in the strictest sense. In this project, we implement a full 4D tensor system using NCHW layout, forward and backward propagation for every layer, a clean sequential model API, training, evaluation, logging, and model saving. No framework, no neural network libraries, no shortcuts. Every operation written manually in C++. Most machine learning projects rely on external libraries just to load images. This one doesn't. Here, the images are loaded using a custom Grayscale JPEG decoder implemented completely from scratch. That means parsing JPEG markers, decoding Huffman compressed data, applying quantization, producing raw pixel values manually. Every digit fed into the network is decoded by a custom C++ code. On top of that foundation, we built a real convolutional neural network. The architecture includes conv2D layers, a full forward and backward pass for layers, ReLU and Softmax activations, max pooling, fully connected layers, Dropout, a Cross-Entropy Loss, and an atom optimizer. This is not simplified math. This is the same logic used internally by real deep learning frameworks. The model is trained on 37,000 MNIST images. 80% of the data, about 29,600 images, is used for training. The remaining 7,400 images are held out for testing. The network is trained for a small number of epochs entirely on CPU. Although the model is trained on only half of the standard MNIST dataset, after training, it reaches about 98% accuracy on the test set, on images it has never seen before. This confirms that the entire pipeline is implemented correctly. Over the series, you will learn how tensors are stored and accessed in memory, how convolution really works, forward and backward, how gradients flow through a neural network, how optimizers like Atom actually work under the hood, and why numerical stability matters. By the end of this series, you won't just use neural networks. You'll truly understand how they work. Right after the first video, the entire project will be available on my GitHub. The code might have a few unused bits scattered around, or some minor bugs I haven't caught yet. But as I create the videos and dive deep into explaining every piece, it'll all come into sharper focus. I'll keep updating the code on GitHub along the way and let you know whenever I fix or improve something. You'll be able to explore the full source code, follow along with the series, run the project yourself, and experiment freely. Everything we built here is fully transparent, so you can learn by reading, modifying, and even breaking the code on your own. We're not just training a model, we're building the entire engine behind it. In the next video, we'll get started with the tensor.hpp file. This file is included in most of the other files, so it's a great place to begin. Okay, let's bring this neural network to life. I'll see you in the next video.